Oh, hello everybody. Let's look at some independent dependent events and then conditional probability. We are actually going to split this up into two videos. First piece here is going to be conditional probability. So those of you who are following along with the notes that I provided, we are going to be kind of skipping some this first video and then we'll fill in the rest the next one. So we're going to start with conditional probability and contingency tables, if I can say that right. So let's start with that. So we'll get to the independent dependent stuff later. I'll use the same slides, but we'll just fill in the rest. So conditional probability, if I can select it, there we go, gives us the probability of an event occurring given that another event has occurred already, or we're assuming that this other thing is happening. And we use some specific notation when we do that, where we say the probability of an event A happening given event B has already happened. So this little line here we can kind of represent as given. So A event happening given B event already did happen. Okay. And we'll get into like the specifics of what kind of goes in top and bottom or what that's going to look like. But before we do that, I kind of want to give you an understanding outside of that. Meaning, let's just use a example here with a six-sided die. So if you're on the notes, we're actually on the top of the second page. We skipped all of the independent dependent stuff. Again, we're going to fill that in later. So the top of page 2. So when we think about this, let's say our sample size, let's just call it S. So here you can start filling this out. If it's a fair six-sided die, we get the numbers 1, 2, 3, 4, 5, and 6. And let's assume that each one's equally an option. Let's call event A, let's call that 1, 3, and 5. And then let's call event B the numbers 3, 4, and 5. Okay, so there we kind of have our situation. We got a six-sided die. Event A is 1, 3, and 5. Event B is 3, 4, and 5. So I want to know what the probability is. Oops, I don't want an equal sign. I want to know what the probability is for A to happen given B has already occurred. Okay, well, without having to do a big formula and everything like this, we can kind of break this down logically. If I'm assuming that B has already happened, I'm basically taking my overall set of values or possible things that could happen, and I'm shrinking them down to simply just event B. Okay, so that changes my possibilities. I only have 3 options for that occurring, for my possibilities. Okay, now if I want to know, well, what's the probability of A occurring if B is of A happening if B's already occurred? Well, let's look at the intersection. Where is the possibilities for A happening? Well, there's only 2 options that A has, is 3 and 5. They both share that, or they both are given that value. So that means out of the 3 possible events for B, I have 2 possibilities for A occurring within that little subset. So the probability for A happening given that B has occurred is 2/3, which should make sense. We're just shrinking down our possibilities, which is what a conditional probability does. We change the conditions of our overall options to a smaller subset and then use that to figure out what the probability is. Now I can use a formula and I can get the same thing as this if we have a little more complex situations, but because we have something like this, let's say, so here's the formula for our conditional probability. A given B, what we use is the probability of A and B, or A intersect B, all that over the probability of B. Which really, when I was describing that, that's what's happening. We're saying, where's the intersection of A and B? Well, that's 3 and 5. And then where's the probability of B? Okay. Well, we can use this with our regular set if we're just doing this. The probability of B occurring is 3 values, so 3 out of the total 6. And the probability of A and B occurring at the same time, well, again, we only have 2, is 2 of the possible 6. Hopefully you can see that the 6's will cancel out, because if I want to get this out, I would multiply by 6 on both of them, so then I'd be left again with 2/3 for the same way. But formula-wise, if we want to use conditional probability, that is this. We're using the intersection, the probability of A intersect B, and then the probability of B occurring. But we can a lot of times think about this logically to do it that way. And we can use what's called contingency tables. Now that makes our lives a lot easier, and I'll show you how we can do that. So let's use a situation here, where this is now just you can look at this and say, well, this is just a table. Yep, this is a contingency table based off situations that we have. This is you can use this to find the probabilities. So I've broken it down to female, male. We're saying out of a group of 130 people, you'll always have these totals at the end, and you need that to be able to write your probabilities. Out of the total 130, here's the breakdown of males and females, right-handed, left-handed, so it just organizes your data a little more easily, and it gives you a chance to be able to find it. Okay, now there's a couple things that we can kind of think of. So if you want to note these, it's not that big a deal. We're just kind of exploring this. Each one of these boxes being in here, these ones, all 4 of those individually are called joint probabilities, which should make sense because we're joining right-handed and female. That's the 58, so that's a joint probability. Left-hand, female, and all those total. All of them together, so if I were to put all of these together, that's called a joint probability distribution, because it's distributing the total 130, because if I add 58, 13, 47, and 12, I get the total 130. So this is jointly distributing the probabilities of each that's going on. Okay. Likewise, we also have some stuff going on this side, these 2 and these 2. Okay. Now these are called either, we can define each one of these boxes individually. We call these either simple or marginal probabilities, where they're just taking into account part of the data. So in this side, we're just accounting for male and female and disregarding right-handed and left-handed, and vice versa. We are only regarding left-hand and right-hand and disregarding male and female. Okay, and those together are marginal distributions. And again, they all equal up to the total. Now, you can sometimes see these contingency tables as percentages. So you'll see you have a blank piece on the bottom below all these numbers. If you want, you can pause the video and do the percentages, see if you get what I get if you want to. Otherwise, you can just fill in now. Okay? Oops. And so here's the same table as a percentage. And you'll see that the same kind of thing is holding, except now the total is just going to be equal to 100%. And everything else is broken down accordingly. But you'll see that the joint distribution now is broken down in our percentages, but still equals 1. And same thing with our, with our marginal distribution. That also will give us our 1. So I'm just showing you different ways that we can see contingency tables in that sense. Now we can also use those to answer some easier questions in terms of things that we've dealt with already instead of conditional probability. So just humor me here a second. So we can find things like, let me get some more space. Let's say, what's the probability that we have a male? Well, I could, given if I had a little paragraph about what's going on, I could find it that way. But if I have this contingency table, I can simply just look at where those things are. So if I want the probability of male, here's my males there. There's my probability. Okay, I do that out of the total, 59 out of the 130. Or if I did it as a percent, I already have that set up. So I can either think about this as 59 over 130 or 45%. Okay, So it's just an easy way to get my data, and I can do that with any of them. If I say I want a left hand, right hand, female, whatever. I can also do that with unions and intersections. So if I want to say what's the probability I have a male and left hand, so that intersection. Well, I can simply just find that's a joint probability. So I go to my male and I look at left hand and I realize that I'm here. So I can think about this both ways. I either have 12 over my overall 130, 12 out of the 130, or since I already wrote it down, I can say that's 0.9 or simply just 9%. Okay. Now the place where I think this is getting useful before we start doing conditional is if we do unions, because that's the or. So the probability of, let's just flip this to a union, or left-handed. If you were to do the formula piece, which we've done previously, you have to multiply or add we have to add our probabilities and subtract the intersection. Well, I can do away with that by just looking at, here's my male, right? I can also think of it on here. And then my left hand. So I'm simply just having those pieces here. So I could just use this to just add all of these pieces up, where I have 0.1, 0.09, and then add another 0.36. So I know that total, this would be, let's see, 45. This would be 0.55 or 55% from that. So you can see how this can be really useful, these contingency tables, not just for conditional probability, but that's what we're going to focus on, because that's going to be helpful for us instead of just simply using a formula to do this. Okay, so let's use this with conditional probability. And again, conditional probability has something that we are assuming already is true. So let's use that as the probability of that we have a male, given we already know we have it as we have a right-handed person. Okay. So why don't you take a second, if you want to give it a shot, why don't you think about that, see if you can come up with a ratio or a percentage, and then we'll come on back. Go ahead. All right. Now the reason this is conditional, because it makes us zone in on a certain thing. So given it's a right-handed person, that means the only thing I care about is this. All of this other junk, all of this other junk I don't care about. So this is gone, this is gone. That's the only place I'm living here is what I'm already assuming is true. So that's what the conditional piece does. It brings in where kind of my world is with all this stuff. So given it's a right-handed person, so again, I can start changing that to know that I'm only dealing with 105 people. So given that it's right hand, what is the probability that it's male from there? Well, the male, we can see, it's right here. Oops. 47 over 105, which I can do, which gives me let's call it 0.45 or 45%. So that's the probability, given that I already have right hand, that I know that they're right-handed. What's the probability of it being a male? Okay, so the way that this does this we can disregard some things based off what we are assuming is already happening. So why don't we try another one here? Why don't you go ahead, let's tell me what the probability is of a left-handed person, given that we know it's a female. Go ahead and try that out. Give it a ratio or percentage. All right. So again, if it helps you, let's see what we're talking about. So we're given that it's female. Well, that means we're only living in this little world. All the other stuff we're disregarding. Okay. I guess I can put it up on here too. So that means that the total that we're now dealing with is simply just 71. Okay, and what's the probability that it's left-handed given that it's female? Well, the left hand is 13. So that means I'm dealing with 0.183, or let's just call it 18% about. So there's an 18% chance that I'll have a left-handed person given that it's female to begin with. Okay, so that's how we're using our contingency tables to be able to find out our conditional probabilities. I'm going to give you two more, and I want you to try that, and then we'll call that kind of a day here for us. So there's only so many combos we can do. So let's go, why don't we flip it around and see what happens with that. So let's say there, and then let's try it again where we have, let's go right hand, given that we know it's a male to begin with. Okay, try that out. Okay, so let me erase, oops. Okay, let's figure this out here. So again, if it helps you, so we're dealing with left, so on the top one here, left hand, so the only thing that we care about is this right here. Everything else kind of fades away for us. So we know that we're dealing with a subset now of just 25 people. We want to know what's the probability, given that it's left hand, that they're female. Well, that there's only 13 female that are on there, so 13 divided by 25 gives me 0.52, or let's just call it 52%. Okay, which was different than the other way. So you can see that whatever we're assuming can change our values there. So let's try the other one here. So male, let me change my color. So we're going male that way. And that means that we're dealing with only kind of a subset of 59, and we want to know the right-handed, which is 47. So let's see, 47 divided by 59, 0.796, so let's call it 80. It's right about 80%. Now you could use, I guess I haven't been doing this whole time, you could do the same thing with your percentage piece here. So if I were to do that, so let's go as our ratio, so 0.45, and then male, so over 0.36, and we should get the same thing, 0.36 divided by 0.45. Yep, and because it's rounded to begin with, we get 0.8 or 80%. So we can do either one. That gives us the same representation of our probabilities. Hopefully that helps, guys. That's conditional probabilities with contingency tables. I got some practice on that. Please watch the other video before you start that practice, because we're dealing with what we call independence or dependence, and we have some small pieces on that. So go ahead, enjoy the next video, and we'll see you in a minute.